Okay, that is why the direction is so if our analysis, so this direction is when we analyze left to right. Okay, so we analyze, so this is our left, and then it's going towards the what? The right. So that's why that orientation. Later on, I'll help you recap when we go into shear force and bending moment diagrams more. Okay, so now, so from here, we are going to do static analysis. Right, so the limits that we are forming the equation is 0x to L over 2. So this is basically between point A to point B. This is between point A to point B. So when this is the case, by doing static analysis, anything that is going up, summation of forces in the y direction is equal to 0. So you have P over 2 minus by V as a function of x is equal to 0. V as a function of x is equal to P over 2. So this means from 0 to L over 2, the shear force is a what? It's a constant. Okay. So if we were to draw our bending moment diagram now, sorry, our bending moment equation. So now we are going to do summation about moment in the z direction anywhere at point x is equal to 0. So where we are taking our moment now is we are taking our moment at this red dot I'm drawing now. Can you see where the red dot is? Okay, that's where we are taking our moment. So when that is the case, we will form this equation where we relate to so the P over 2 will generate a clockwise, so minus P over 2 or minus Px over 2 because it's a distance. So force P over 2 multiplied by distance is negative because it's going clockwise, plus by m as a function of x, the whole thing is equal to 0. So from here, we know that m as a function of x will be equal to P over 2 multiplied by x. Okay. So this is for between A to B for simply supported beam. Now let's go into a cantilever beam now. Okay. So if you look at a cantilever beam, if we say that it's equivalent, mathematically the equation has to be the what? The same. Okay. No doubt physically it looks very different, but there's some similarity on it. I've shown to you one of the similarity is what? Is that the failure will be at point where? The failure will be at point B. Okay, I'm turning off my camera because there's nothing to see. Okay, you guys are just looking at the sky. So you can see that physically it's different, but the similarities is that failure will both occur at point B. Okay, and then I'm going to show you mathematically it's also the same. Okay, so how do we do that? So we are going to look at the cantilever beam now. So I'm going to move the cantilever beam, and some of you will focus. Oh yeah, the equations are the same. All right. So we are going to look at we're going to form the equation likewise. So we're going to go from point A, 0, x to L over 2. So this is between point A to point B. So again, if I were to draw our free body diagram, so this will be equal to P over 2. So this is our point A, and then we have a slider, a variable V as a function of x, m as a function of x. So when we do that, so again we do static analysis. So I mentioned about forces in the y direction is equal to 0. We have P over 2 minus V as a function of X is equal to 0. V as a function of X is equal to P over 2. Then we have summation about moment in the Z direction anywhere, or the reference point is at point X. So we're going to take moment exactly over here at the red dot where we take our moment. So we have P, so it's going clockwise, minus P over 2. Okay, minus P over 2 X plus by M as a function of X is equal to 0. So now M as a function of X is equal to P over 2X. Exactly the same mathematically. The shear force and bending moment is exactly the same within the same what? Limits. So this is why, okay, this is why we say that the cantilever beam, okay, the cantilever beam and the simply supported beam, when the load is acting exactly at the center, these two structure is exactly the same. That's why when we have a simply supported beam, we only look at what? One side. We don't look at the other side. We will just say, okay, we're going to analyze this side of the structure. We don't analyze, okay, let's analyze from A to B, then we go to B to C. Okay, we don't do that. Okay. So if we were now, if we were to now to construct our shear force diagram, okay, so our shear force diagram. So I'm going to change my paper now. If we were to do our shear force diagram, okay, I'm going to draw the full length. So this is X. This is your V shear force. So what we realize that, and then I'm going to call this 0, and then we have L over 2. Okay, 2, and then we have L, right? So when we were to construct now, or to draw this out, we know that it will come to here. Then at L over 2, it's going to come down by P. And then you go this way. And then it will go back up P over 2. Okay, so this is your shear force diagram. So this is your shear force diagram for simply supported. Okay. So this is over here is your positive P over 2. And then down here will be your minus P over 2, right? And then on your bending moment diagram, X, like over here, you can see, right? We from our equation over here, we have V. Okay, so this line over here is basically V as a function of X, and this is equal to P over 2, right? And then we draw our bending moment diagram. Okay, so this is our bending moment diagram. Bending moment diagram, I'm only going to focus on more positive. Okay, so likewise, we have our L over 2 over here. We have our L over here, right? Then we know that this will peak, comes to the very top, and then after that, it will come down this way. Okay, so over here, this is your moment equation, moment axis. So this expression over here is M as a function of X, and this will be equal to Px. Okay, so this will be equal to Px over 2. And at this point over here, right, is equal to PL over 4. Right. Can someone tell me what is the relationship between the shear force and bending moment diagram? I know we are doing pure bending, but I want to recap this very quickly. Not very quickly, but I want to recap this so that future courses you will have less problem. Okay, anyone can tell me what's the relationship by looking at this diagram?
Moment, Eugene. Moment is the derivative of the shear force, the moment diagram.
Okay, you are giving me a mathematical expression now. Yeah, absolutely right. Okay, when you integrate when you integrate your shear force, okay, so when you integrate your shear, so what you're telling me, Eugene, why not a moment is equal when you integrate, okay, to your limits 0 to x1, right, and you have v as a function of x dx. When you integrate, this will be equal to, so when we do this, 0 to x, right, p over 2 dx. So this is equal to px over 2. I'm not saying you're wrong. You're absolutely right. Okay, but look at this diagram. Tell me, what trend can you see? Anyone? What trend can you see? So I'll give you a hint, okay? So when you guys know this, okay? When shear force is equal to 0, what will happen? Anyone? What will happen when shear force is good? What's happening at L over 2? Can someone tell me, please?
You have your maximum bending.
There you
Moment.
go. Yeah, you guys are remembering now, okay? Where shear force is equal to 0, there is a possibility that bending moment is at its what? Maximum. When I say possibility, because sometimes your structure can have can cross 0 at a few location. Okay, so you need to check. What's the other thing that you can see? Anyone, please? What is the other observation that you can see? With these two diagrams? Anyone?
When bending moment is 0, shear force is max or min.
You're trying to be creative. I like that. What else? I mean, that's very similar to what we've just written earlier. What else? What can?
The value of the shear force is the slope of the moment diagram.
Well done. Okay, so I'm going to write this down. So the magnitude of the shear force. Sorry, is it the magnitude? No, the magnitude of the shear force is equivalent to the slope orientation in the bending moment diagram. Okay, it's equal to bending. So i.e. over here, the magnitude is positive, right? Over here, you can see that the slope is positive. Over here, your magnitude is negative, your slope is also what? Negative. Okay, so that's where when we form these equations, okay, when we form any of these equation, we know that this is positive, and over here this is the slope. The slope also has